Hello and welcome everyone to today's webinar, which is Advancements for Millimeter Wave Antenna Design. My name is Naveen Kumar and I am an application engineer at Remcom. And today I'll be taking you through some of the latest features that have been added to XF 7.9.1 that makes millimeter wave antenna design much easier and efficient. To start off, I would like to give you an overview of the topics that I'll be covering in today's webinar. So the first two features, which are singularity correction and multiport CEO for integrated circuits, are post-processing, singularity correction, which is mostly a major feature, which is added to XF 7.9.1. And multiport CEO is a post-processing feature which now allows integrated circuits to be characterized and simulated in XF. And following that, we have three usability related features, that is advances in PCB import and the capability of replacing materials for different parts in the CAD model. And the third one is the sampling breakdown results for ESD analysis. And in the end, we would be covering the power density optimization for codebooks. And as for the questions during the webinar, we have a GoToWebinar window, which you can use to type in any questions you may have during the webinar. And I'll have my colleague, Sam Seidel, who would be able to answer these questions for you. And if there are any questions left over, then we will have a Q&A session in the end, where I'll be addressing any other questions that you may have. The first feature we have is the singularity correction, which is an advanced meshing option in XF that accurately captures high varying fields at the edges of a conductor. So what XF now does is it smartly handles the electric and magnetic field values adjacent to metallic edges during time stepping, which actually reduces the runtime by great extents and enhances the accuracy of the simulation. To demonstrate this, I have a 79 gigahertz radar project that I will be showing you today. So here I have a snapshot of the same radar with 4 patch antenna elements that are series fed, each containing 8 patches, which is actually fed through these transmission lines coming off of a chip. And I am going to show you two different simulations which were performed on this patch antenna array. So the first one, which uses the traditional FDTD grid, which assumes a linear transition of fields between the cells. But in case of such conductors where we have high field variations at the edges, we would now have to use a much finer grid to characterize or efficiently get track of the fields which have high variations at these edges. So for that, we will have to go through a small cell sizes. And in this case, we have a 10 micrometer cell size, which is being used. And this would take a lot of simulation time. And now I have a second simulation which I have run on this patch antenna array with singularity correction enabled. And as you can see, this enables us to use a much coarser grid even at the edges of the conductor where we have high field variations, which increases the time step duration and reduces the overall simulation time. As you can see the comparison, the smallest cell edge in this case is 18 micrometers compared to a traditional FDTD grid, which uses around 10 micrometers. Now, I would like to show you the results of the FDTD simulations that I have run. So here to the left, we have the S parameters plot, which is given for the 79 gigahertz array. And I have two simulations, simulation 1, on which the singularity correction was not enabled, which is shown in the blue line. And the red line is results from a simulation 2, on which we had singularity correction enabled. And to the right, we have a table which actually gives you the information of these two simulations with respect to the memory and runtime that was taken and the cell sizes which were used. So for simulation 1, you can see that we require somewhere around 6.3 gigs to simulate this antenna array, and the total runtime which was taken was around 2 hours 21 minutes. And simulation 2 with singularity correction enabled can be seen that we just need 1 gigabyte of memory to perform the simulation, and it takes just 21 minutes to perform the simulation on this radar. And also, on referring to the S parameters plot, you can now see that singularity correction more accurately predicts the null for the S11 and the values in all other frequencies. To demonstrate this feature, I would like to show you the same project in XF. So here I have the same 4-patch antenna element 79 gigahertz array, which is set up in XF. And this has, these are the 4 series fed patch elements with 8 patches each. And we have a substrate below that, and below that is a ground plane, which I have set invisible right now. And these elements are fed with the 4 transmission lines, which are coming out of the chip that you see here. To enable singularity correction on these patches, you can do so by selecting the parts on which you would like to enable the singularity correction on, and right-clicking and accessing the gridding and meshing properties. You now see the enable singularity correction on all parts options, which I will be selecting. And viewing the parts list now gives you the list of all the parts on which the singularity correction is enabled. So you can see the icon here, which signifies the singularity correction enabled on these parts. And similarly, we can look at the parts such as a ground plane on which a singularity correction was not enabled, which is also listed in this parts list. And as for running the simulations, it would be the same FDTD simulation setup that the users are used to. And I have created an FDTD simulation for this array with singularity correction enabled and one without the singularity correction. And here is the S parameters, which shows you the results from these two simulations. So the blue one here again has no singularity correction enabled, and the red one has the singularity correction enabled. So you can see that the resonant frequency is accurately predicted by singularity correction with a much deeper null. And now getting back to the slides, let's look into the second feature that has been added to XF, which is the capability of simulating multi-port devices in XF. So XF with the circuit element optimization now supports integrated circuits or chips such as impedance tuners, switches in XF. So with the transition from 4G to 5G, the new devices that would be coming up will relatively have less real estate in the device to fit in a lot of antennas. So in that case, we would make use of chips such as impedance tuners to use the antenna for different bands and applications. So XF now supports these chips, which can have more than 2 endpoints. So as an example, I have an impedance tuner that makes use of 2L matched networks. and a tank circuit here. So this chip can have multiple states with which you can choose a proper impedance to tune your antenna accordingly to the frequency at which you want it to operate at. And the same can be simulated in XF, and the XF geometry and components are shown to the right, where I have set up a similar or the same schematic represented in the left within XF, which I'll be showing you in the next slide or in the demo. So I've created the simulation results for this chip. So one of the problem statement that is created here is to tune this antenna in different LTE bands. So without the tuner or any of the impedance networks connected to the antenna, we would have it operate in the LTE2 band, which is shown in the green curve in the S11 plot to the right. And similarly, to have this antenna tuned into a LTE30 band, now we use one of the states of the chip, which enables inductor and capacitors connected across it, which can then tune it to a LTE30 band, as you can see in the blue S11 plot to the right. And similarly, on enabling a different state of the chip, you can now tune the same antenna to operate at LTE band 7 with a different combination of capacitors and inductors connected across it. And to the right, you can see the red plot, which now has the antenna operating at LTE band 7. Let's now look into how this can be done in XF. So here I have the antenna connected to a ground plane, roughly as large as an iPhone 8. And above this ground plane is a substrate. And in the corner is where we have the antenna. And to this antenna, we have the same chip, which is an impedance tuner, which is connected. And these this components that you see here are the schematic representation of the inductors and capacitors. So what we would do in XF is run a response matrix, which characterizes each device's connection or each of the connection into this chip, and then run a CEO optimization, which then makes use of a .snp file from the manufacturer of the chip, which actually contains the different states at which the chip would be performing. And using these, XF would now allow you to accurately simulate the performance of this antenna uh, to know how it performs in these different chip states. And having performed the response matrix and CO optimization, here is the S11 plot for the same antenna. So as you can see from the results, so the green line is where the antenna is tuned to LTE band 2, and the blue line is now having the antenna perform at LTE band 30, and the red line now has the antenna tuned to operate for LTE band 7. And coming back to the slides, let's now look into the next features that have been added to XF. So the following three are the usability related updates which have been added to XF. So let's start with the advances in PCB import. So now with the PCB being imported into XF, we support two other components which also would be brought into XF. So we start off with importing document layers or silk screen data or any sort of text within the PCB files representing some sort of information can now be imported into XF. And the other import feature is the ability to import any sort of components. So within the ODB++ and the BID files, there are definition and locations of different circuit components like resistors, inductors, or capacitors, or even other complicated chips. So we can now import these components into XF and place them accurately in the space, in the simulation space. The second feature is the ability to replace materials for different parts. So within XFdtd, when a CAD model or a PCB geometry is imported, the different parts on these models were imported with a different color scheme and with the default material names. And with the capability of replacing materials, we can now replace these materials of the CAD models or PCB geometries with different materials from the library or a user-defined material, which greatly simplifies the workflow of characterizing these devices. The third usability related feature that we have is the capability to sample the breakdown results. So within XF, we use the dielectric breakdown sensor to characterize any sort of electrostatic discharge analysis happening on a PCB. So the breakdown sensor, what it does is it monitors all the FDTD cell edges in the simulation space, and particularly tracks the E fields in these cell edges and compares it to the dielectric breakdown strength or the dielectric strength of the materials. And once if the E fields are exceeding these dielectric strengths, so all these cell edges would now be monitored or would be showing you the locations where there was a breakdown that happened in the simulation. So we now have a capability to just use a part of uh, simulation time where you can monitor the dielectric breakdown. To demonstrate these features, I would like to import a PCB into XF. So here I have the XF import log of a ODB++ file, which gives you the details of different layers on the PCB. So previously, XF was not letting you import all these data, such as the silkscreen data, which you can see on the right. And also, this can contain any sort of solder paste or any mechanical layer information that is contained in the PCB, which would now be imported into XF. And there is an additional tab, which is the components tab, which lists out all the components that are present on the PCB. And you can select all of these to import these into the XF simulation space. So in this case, let me go ahead and import this PCB into XF by naming the PCB. And to save us some time, I already have this PCB imported into XF. So as you can see, with the different layers and components selected on the PCB import dialog, this now imports the PCB with different document layer information or silkscreen data information. And when these data are imported into XF, so they will be unmeshed, so not included as part of your simulation. And to show you the other features, I will set this invisible. And the second feature that I would like to show you is the circuit components which were imported into XF. So as you can see, there are a lot of capacitors and resistors which have been imported into XF as part of the import process, which were contained within the PCB. And for each of these components, XF now provides a circuit component definition with its appropriate resistance, inductance, and capacitance values. So the next feature that I would like to show you is the capability to sample the dielectric breakdown data. So in most of the ESD simulations, we would be using a human body model waveform, which is similar to the one that I have on the screen, which is a double exponential function. And in these kind of simulations, or in these kind of tests, it's usually possible that we see ESD breakdowns at the peak of the waveforms. So it would not really be useful for us to monitor the breakdown happening in the first half of the, or until the waveform reaches the peak. So what we can do in this case is use the dielectric breakdown sensor. So in this case, I am opening up the dielectric breakdown sensor definition editor, where I can actually now set up the start and end time for the dielectric breakdown monitoring for the dielectrics. So in this case, I can maybe have it monitor the breakdown happening between 0.2 nanoseconds to 1.2 nanoseconds if needed. So with these settings, we can greatly reduce the simulation time and also monitor the breakdown at the required instances. And the next part that I would like to show you is the ability to replace different parts in the PCB. So as you can see, this PCB has a substrate material, which is an FR4, which is used. And in case I wish to change this material, we can do so either by creating a new definition under materials, or accessing a different material from the set of materials we have in the XF library. And in this case, let me go ahead and use a Rogers 4360 material with which I would like to replace the substrate material. So here, let me open up the definition of this Rogers material and enter in the required material frequency. And to replace the material, what I can do is select the substrate material and replace it with the Rogers material here. Select the material, and now with that, let me actually go ahead and change the color of the material so that it's okay, clearly evident. So in the appearance, I'm just going to change the color of the material. So you can now see that the material was replaced with the Rogers material here. So this greatly speeds up the simulation workflow for different simulations that needs to be performed. And coming back to the slides, the last feature is an analysis type. So as we have specific absorption rate to predict RF penetration into the tissues at low frequencies, we similarly have power density, which is radiation exposure assessment that is used at high frequencies between 6 gigahertz to 300 gigahertz. So what this does is, at high frequency, we are morely interested in the RF exposure over an area rather than the deep tissues. So this is a standard which now measures this RF exposure over a surface. So REMCOM is part of this committee, which is working in the development of the power density standard. And the power density standard would be finalized by end of next year. And currently, there are two drafts that are available, the committee draft and the committee draft for vote. And XF is consistent with both of these drafts. And using these drafts, we have an example here on which we have the part showing you how the power density can be computed. So I have a mobile phone with four element antenna array in this example, and an evaluation plane which is placed some distance away from this phone. And in an FDTD simulation, we would be tracking the E-fields on this planar surface, and then use that to compute the power density or over the different parts on this plane. And also XF 7.9 previously supported the codebook capability, which which could be used to characterize the different states of a millimeter wave array. So as part of optimization, so there is a pre-processing which is now done on the evaluation plane before computing the power density for different states on the codebook, which greatly speeds up the process of power density computation in XF, which is now included in 7.9.1. With that, I would like to wrap up the slides and the new features and the demos that I wanted to go over. And so now I would like to open it up for any questions. So let me look into the chat window or the questions window to see if there are any questions. Okay. Okay, there are a few questions that we have here. So, okay. Okay, there is a question. Do we need encrypted chip models for the multiport CEO feature? So no, actually we would not need a encrypted chip model. Rather, it is more of getting a S parameters file for different states in which the chips would be operated at. So having this file would be sufficient to simulate the performance of this chip within XFdtd. Okay. And values are calculated. And the next question is, okay, what are some of the parts on which the singularity correction can be enabled on? So singularity correction should be enabled for critical metallic design components where you have a strong and rapidly varying E and H fields. So the antenna radiators, so for example, for a patch antenna, the radiator would be a, a, a component on which you would want singularity correction to be enabled, or any sort of transmission lines which are nearby, and also for resonators. So are there any drawbacks to using singularity correction? So if you are particularly looking into drawbacks, I can check with our engineers particularly on that, and maybe get back to you with more details related to that. But one of the things that I can let you know here is singularity correction would be more efficient if you're using that with high frequency simulations. But if you actually see, they perform in the same manner for applications in both low and high frequencies, but you would see more pronounced advantages of singularity correction for millimeter wave applications. So how do the codebook values are calculated? So the codebook values can be calculated from one of the features that we have, which is the array optimization, which with which you can actually provide the directions at which you would want to point the beam at, and from that you can arrive at the different phases and parts for the different ports, which in turn gives you the values for each of the entries on the codebook. Also, you can get these values empirically if available. Okay, and another question we have here is, can exact and singularity correction be used together? Yes, both of these can be used together, but singularity correction will be enabled only on those cell edges which are aligned to the conductor edges. Okay, if you change the substrate on the radar example, how does the performance change? So I'm assuming this is a question based on how the singularity correction results would be changed. So since you're not really enabling singularity correction on the substrates, so the way at which the results would be computed would still be the same, but based on the substrate, we would just have the field variations which would be changing, and these are actually modeled more accurately uh, with with the model, as in, like, it just changes the field variations happening in the patches. So those would be more better accounted when the singularity correction is enabled on the patches. So substrate wouldn't really have much changes on the singularity correction features. So how can we get a trial version of the XF? So to get a trial version of the XF, you would have to contact our sales department here. So in the end, I would actually provide you the link for that. So you can contact us at sales@remcom.com. Okay. So with that, I think we have most of the questions answered. So, okay. Okay. So will we be getting a copy of the presentation? Yes, this is something that we've not done in the past, but we can definitely do it. So please contact us at our sales@remcom.com, where we would actually be looking into your request and look forward to how we can address that. Okay. So with that, I would like to wrap this webinar up. I would like to thank everybody for coming. You should be looking for a copy of the webinar, which would be emailed to all the attendees, and you can share them with your colleagues and let us know if you have any questions. And if you are interested in knowing more about the features, you can visit us at or visit our support site at support.remcom.com. where you have more information related to any usability or scripting performance related updates that have been added to 7.9.1. And to get the free trial, so here is the link on how you can get a free trial and getting to know more about the pricing options. And if you have any more inquiries, please feel free to contact at sales@remcom.com. So with that, I'd like to sign off. And thank you everyone once again for attending today's webinar, and have a great rest of your day.